the functions for all possible actions, the maximum of the output of the function for all possible actions. So in this case, it will be the policy will be, we already discussed this, I'm just formalizing it more. It will be 50, 25, 12.5, 20, and this is 40, and that is also 100. So that is your state action value function. That's your Q. Now I'll what they call write an equation called the Bellman's equation. Is basically Q of S comma A. S and A are my states in action. I'm basically passing. See, as you can see, like the definition says, you start a status, take an action A. So these two are my input variables, S and A. So Q of S comma A, like the formal. I'll write the formal definition. 1 second. The formal equation. It is where is it? Okay, like it is basically Q of S comma A is return that you get at the reward that you get at state S, right? And then times the gamma, and plus gamma times the Q of S dash comma A dash max A dash. Do you guys understand this equation? Basically, suppose you're at state S, you take action A, you collect the reward. This is my reward at state A at state S. And then you're scaling the remaining rewards that you get by a factor gamma, and this is basically the maximum of Q for the next state S dash. You after you take an action A from state S, you reach S dash. Remember the tuple which I defined some 10 minutes ago. So you find the maximum. Basically, this means that the return that you get from the following optimized path, the return that you get from the optimal path, from the following optimal path. Is this clear? Bellman's equation. Like from the definition, is very intuitive, right? You are at basically the function, the return that you get when you start a status and you take an action A is basically the addition, the sum of the reward that you get at status and the return that you get by following the optimal path, which is basically the maximum of the function for all the actions A dash, for all the action A dash which you will take when you reach state S dash, which is the next state, right? Yeah, S dash is the next step. Okay, so I hope that's clear. Okay, what else is there? Do I need to is this very clear to all of you? Okay, I need a raise of hands if you guys can tell, because do I need to show it to you that this is in fact true by taking examples, or how? Fine, right? So I guess I can skip this part. Fine. Okay, so now we had 6 states. We had a discrete number of states, and this is a very simplified version. Now you have a helicopter with you. It has many states possible. There are infinitely many states, right? For every small change in angle or every small change in position, you have a preferred action which will differ from any other states, right? So now now things get very much complicated. So we coming to continuous spaces. And let's define what the variables are, what the possible variables are for the states. Like suppose you have a truck or you have a helicopter. So can anyone tell me how you will, what are the coordinates required for uniquely determining the state of the helicopter? What coordinates are required, like position, velocity, all that? And consider 3-dimensional only. Anyone? Right. Come on. Like for truck, it was x dot, y dot, and theta dot, right? The angular velocity. So what about for a helicopter? It will basically be x, y, z. is a three-dimensional. We're considering a three-dimensional space, and then the velocity is along the axis x dot, y dot, z dot, and then there are now three angles with us. Yeah, exactly. So theta. What else? It can tilt like this. So theta, and it can like move. It can like tilt about its z axis. So I'll call that phi. And what else is there? Okay, for now, assume this is it. And their velocities across these rotations. Right. So these all are my states. I mean, these are all my variables through which you can define a state. Right. So now you'll try to figure out it's the policy for a helicopter, or basically try to figure out what the Q is for the helicopter, what the state value function is for the helicopter, state action value function is for the helicopter, and then for each state you'll find the maximum of the function across all possible actions, and you'll define that as your policy. So our first step will be to find Q of s comma a, and then take maximum and find policy, right? So our goal is to find Q of s comma a for all the states and all actions that correspond to that state. Okay, so we'll deal with the example which I learned, basically Mars rover example. And suppose this is my display screen. Okay, and these are my two, like this is where I want to land. Okay, and these are my two posts which basically bound the territory at which I have to land. Okay, and this is my Mars rover. It looks like a UFO. Okay, and I want to land here. And let's say I have a thruster here, I have another thruster here, and I have a thruster here as well. Thruster is basically you'll fire the thruster and you'll move in the opposite direction. If you fire the left thruster, you'll go to the right side, right? So can anyone tell what actions will be there for this Land Rover? Hey, come on, guys, we need discussion. Like for any state, let's suppose consider this state only, in which the helicopter is that I've drawn right now. So what are all the actions possible? You have three thrusters with you. So hello. Anyone? I mean, if you guys can like write left or right, and left, right, and away from the post. True, correct. But what I mean is action that the Land Rover should do. It has three thrusters, right? So what can do with those three thrusters basically? You're correct. Like left, right, away from the post is basically if you want to go left from the, if you want to move right from the left post, you will fire the left thruster, right? So our actions will basically be first fire the left thruster, okay. Two will be fire the right thruster, and the thruster which I drew at the bottom, this one, this is the main thruster which like helps you to fly up. Okay, so fire the main thruster, and four is like just do nothing. Why bother? So do nothing. So these are my four actions. And what is my reward function? The reward function is basically, and let me give you an example. So suppose this is my what's that called? Rover, right? This is my rover. It's supposed to land on this territory, and this is the position it's supposed to land in. Okay. Now suppose it lands it is something like, it lands something like this. Somebody asked me this. Did you guys actually understand what I said till now? Like thumbs up or something. Okay, so basically what I'm saying is, see, you have a randomly initialize your Q of s comma a from the start. You have, and then you have put you have trained your model, gotten the parameters for this neural network here. You've gotten the parameters for this neural network here, and but your q of s comma a is still whatever you have randomly initialized. Where is your your final output, right? So what will you do now? This is your random initialization which you had at your start. So anyone can tell what will you do, like how will you proceed? You just did it once. You just did figure out what you just figured out what the parameters would be for your model when q of s comma a is randomly initialized, and you don't even want that because that's just random. You don't know what the preferred actions will be for your states. So any guesses, like what will we do? Come on, does someone? Basically, what you'll do is like you will repeat the process again. Okay, you will again randomly generate 10,000 inputs. Basically, randomly generate 10,000 s comma a's. Okay, and you will feed in y as x and keep doing it till it is steady. Exactly. We'll keep doing that till it's steady till our q of s comma a finally converges. Right. So we did it once. We'll again randomly generate 10,000 inputs s comma a, feed it into the neural network. Okay, and then our new see what we're going to do is that again training the model. We're retraining the model with new values of q of s comma a that we got from our previous like train from a previous training. We got new values of q of s comma a, right? How? Because for each new input you give to s comma a, you can feed it into the what's it called, this neural network, and get the corresponding q of s comma a and use that to train all the parameters, all the training examples. And you'll repeat this till your q of s comma a converges, till it is stable. Do you understand? Okay, so yeah, basically, and our algorithm will be first initialize a random guess of q of s comma a, and then you'll repeat this some number of times. Some means it can be, it depends on you, your parameters, your gamma. There are many algorithms in this. There is some epsilon greedy policy, and what else? There are many mini batching, and what else is there? Your soft output. See, yeah, all these algorithms are there, and each of these algorithms, and when you combine all these algorithms, your model will become very complicated. But it helps you to reduce the time in which your model is running for, because if you repeat, see, you already have many training examples. You're firstly generating 10,000 training examples for each run, and then you're repeating this. I'm not sure how many times you'll repeat this, because it's definitely not going to converge in 10 times or 20 times. You would need to repeat this for around 1,000 times, 10,000 times, and 10,000 training examples is very less. 10,000 times might also be less depending on your application. For landing this simple Mars rover, I guess this is quite practical, like 10,000 training examples, 10,000 repetitions. So, but like it depends, honestly, how many times I have to repeat. So repeat it for the number of times that you are satisfied with, basically. So repeat this algorithm which I'm about to write. So first, yeah. So first I'll generate what? Take action. Basically, like generate 10,000 s comma a comma r of s comma a dash. Okay, you'll generate 10,000 of these, and then you'll put this in your Bellman's equation. Like put in your Bellman equation, okay, which is q of s comma a is equals to, I have written this some 10 times already, r of s plus q max a dash s dash comma a dash, and you'll put it here. You will get your x. Your x is basically s comma a only. This is your y, right? You have randomly initialized your q of s comma a, and then you train your neural network. Okay, and then you will get your new q for the future inputs that you put in to your training model with your parameters that you get after training it for the first time. You can get your Q new, right? So basically Q old is gone. So like Q new will basically be approximately equal to, like, we're not trying to get a drastic change. It will be approximately equal to your the output of the, now the output, it would be the training data, the y of the train data that you give initially, the before this run, whatever this run is, before this run, the q of that should be approximately equal to q new, and then you'll put q is goes to your q new, and then you'll repeat everything. Oh shit, this is the maximum zone. Okay, anyways, so you'll did you guys understand this? The algorithm, like, you first generate, put in your Bellman's equation, get x comma y, train your network, get x new, then put x q goes to q new and repeat. Did you guys get this? Any doubts? Please. Because this is it. I mean, this is reinforcement learning basically. And like, now there are many algorithms that you can do, which I will take. Now I'll be discussing some optimizations and algorithms that you can do to fasten up the process of reinforcement learning. And depending on time, how long do you guys want the session to be? Hey, at least for this unmute and tell the, like, I'm fine to continue. Okay, how about others? It unmute. Anything works, huh? I mean, if someone has an 8 a.m. class, I don't want to unnecessarily, like, screw them over. So okay, let's just see. I mean, if it works for everyone, sure. So okay, first I'll just check if there's anything that's left. Uh, hmm. Okay, so I'll just give a technical term to what we just learned. It's not like we'll sleep now. Lol, yeah. I wouldn't expect you guys to sleep either. So okay, so this is called DQN or Deep Q. Wait, DQN, Deep Q network. Okay, so why is it called this? It's basically you're using deep learning, or basically using neural networks to figure out your Q, your state action value pairs, right? So this is called a DQN. Now we'll see some refinements, like some algorithms. Wait, I'll first zoom this in. No, wait. How do I? Okay, I'll zoom this in and I'll write. Yeah. So now some refinements. So the first refinement that we can do. I told you guys that our neural network was like this, wherein we get a q of s comma a. Our inputs were s a, right? These were 64 units. These were 32 units. This was 1 unit. Now, see, this will take substantial. Like, when we have a lot of actions, in this we had only 4 actions. Now there can be more actions. Like, somehow someone pointed earlier, I guess, can we not, I guess, I'm not sure who, but someone asked me, can we not, like, do 2 actions simultaneously? You can, and you can define a new action for it. Okay, you can define a comma b as in, like, suppose there are 2 actions, a comma b. You can define a new action in which both of those happen as both of them happen simultaneously, and you can have some 20 actions. Okay, like that. So this model, if you do like this, for, because this s comma a, or input s comma a, will differ for, when you have one state you have 20 possible actions, right? So during inferencing there'll be a lot of training data with you, and which you do not want, because firstly you have a lot of training data, and secondly it will take a lot of time, right? You have huge amounts of training data. Your algorithm, to get your squared error, and you add all of them, it will take a lot of time, right? Which is very inefficient. So what our refinement will be is, we'll keep our neural network same, but suppose we have 4 actions. I'll have 4 neurons in my output layer. My input layer will have, will my input layer will only be state A. this will go inside my neural network. My input will go inside my neural network and will get 4 outputs. These 4 outputs are my Q of SA for my 4 states. What are my 4 states? My 4 states are my 4 actions. My bad. These are the outputs for my 4 actions. My 4 actions are either you fire the left thruster or the right thruster or the main thruster, or you don't do anything. Right. So now a lot of, firstly, you have generated lesser training data, you get, and everything, and like you take the time that the model takes to run is also less, and this is only for 4 actions. Think about large scale, like suppose some 10 actions. A lot of time, and firstly a lot of time is saved, and secondly you get higher, like you get a higher efficiency. So, and that's what we want, right? So ultimately this helps. Also, one more thing, in your Bellman equation, we have a term which is Q of S dash comma A dash, right? Maximum of A dash. It helps in this as well, because out of these 4, we need to take the maximum, right? So it's quickly able to do it internally. It's quickly able to find the maximum of all of this. So that is one refinement. Our second refinement is called the epsilon greedy policy. Okay, so that basically, what is it? So basically, remember when I said you have to pick up actions. So you have S comma A, right, which you're feeding it into your neural network. Let's say neural network, you're feeding S comma A to your neural network, but like you want efficient results, you want it to take lesser time, so you cannot feed in all possible actions to your neural network, right? So how do you think I should feed in my action for that particular state? Anyone, like, any guesses? Go for the best action, right? So true. So one option is to go for the best action that you got. Basically, your previous runs or your random initialization, not random initialization. You not go by the random initialization, but you'll go by your previous runs best action for that state, and then you will keep on inputting that to your neural network to get better Q of S comma A for like that state and action, right? So either you do, you always go for the best action. That is one way. Or the other way is you go for the best action 0.5, 0.0 point, the probability that you go for the best action is 0.05, and you wait. Okay, my bad. Why will you go? I'm dumb. Yeah. Why will you go for the best action only 0.05 times? You'll go for the best action a substantial amount of the probability that you'll go for the best action should be a lot, right? So let it be like 0.95, the probability for going to the best action, and let us randomly explore for the rest of the probability. For the remaining chances, you randomly explore, right? For 0.05 times, you randomly explore. You just explore. So this 0.095 is called being greedy, and your this is called this is basically exploration. Yeah. And then basically what am I doing is, see, you cannot obviously go for the best action, because suppose you're always going for the best action from the start. So you have a random initialization of qs comma a, and for suppose always, like, it will basically learn that always pushing one thruster is better than everything else, and it will train your model like that, which is not good, right? So you cannot always go for the best action. You can go for the best, like suppose you have an initial best action with you can be greedy about going with it always for some number of times, for a lot of number of times, for a lot of number of times, and for the rest you'll randomly explore, right? So this 0.05 is your epsilon, and hence the name epsilon greedy policy. Now, what I would suggest is, first you keep a high value of epsilon. I mean, yeah, right. Yeah, you keep a high value of epsilon, because you have randomly initialized. Oh wait, somebody asked one. Go for the, okay. Oh no, never mind. So yeah, you will put your epsilon to be very high. you will basically want to explore a lot first because you don't know what your best action is, and then you'll reduce it. Like you'll reduce it slowly because you'll repeat your what's it called implementation some 10,000 times, right? You'll repeat it, so you'll randomly decrease it till you reach probably 0.05. So from 1 you go the next epsilon you choose, let it be like 0.98, then 0.96, and so on till you reach 0.05, and then hopefully by then the model converges. Okay, so do you guys understand this optimization for reinforcement learning? Anyone? Can you explain the first one again? The first refinement, like when you increase the number of neurons which correspond to the actions for the states in your output layer. For that one only. Yeah. So basically, you are increasing the number of. Firstly, you're increasing the training data that you have, because initially your inputs that you were giving were S comma A, right? A is, suppose in our example we have taken 4 actions. So for every state you have 4 combinations. Okay, and there are many states. There are some. There are, you cannot count the number of states you have, right? Suppose for a helicopter or a truck or anything, you cannot count the number of states. So now your train data has increased, and you won't get proper results because suppose you want only 10,000 training examples, and you have 4 actions with you. So your unique number of states will be 2,500, right? So you won't have what's that called better outcomes. You will need to run the what's that called algorithm a lot of times, and then I mean it is not efficient because you don't have time. You're an engineer, and yes. So what I am saying is, you only give your state as the input to the neural network, and the output of the neural network be the queue of the different actions, and from that you take the best action and define it to be the policy for that state. Your initial values of q of s comma a1, s comma a2, a3 and a4 so on will be random. You will train your model with those random values initially, get new values, train again, do all that again and again till your model converges. Okay, so that was the first policy. That was the first optimization. Second was the epsilon greedy policy. Now third, we have time, no? Yeah. Third, I'll discuss. I'll zoom in. Third is called mini batching. I hope that is the name. Okay, so before we deal with reinforcement learning, for before we deal with mini batching and reinforcement learning, so we'll start with some bias towards an action, and those biases keep changing towards the actions that model suggests more, kind of like evolution. Yes, I think, yeah, kind of like evolution, because we're randomly initializing an action for a state, preferred action for a state, because we're randomly initializing the q of s comma a, and then depending on how your model is reacting, your biases will change, and yeah, I mean your model will evolve basically, kind of. So yeah, mini batching, yeah, mini batching. So yeah, coming back. So let's go back to linear regression. Okay, so in linear regression, hey yo, at least this. Can someone tell what linear regression is? Come on, what is linear regression? Okay, not a straight line, but you can fit a curve to the set of data. Okay, so suppose this is your data. You have a lot of data with you. Okay, oh, charge of the tab is running low. Fine, fine, like. And suppose you have some 10,000 training examples. It is preferred that you do not put all of this into your, like you do not try to fit a curve to all of these whatever 100,000 training examples that you have. It will be preferred that you split them into batches, fit a curve, and then run gradient descent by taking different batches. Did you guys understand whatever I just said? I'll write it. So suppose you have 1, 2, 3, 100. These are all my training examples. 1, 2, 300, 200, 1000, and then so on till whatever this is, 1000. So yeah. So what I'll do is, this is my. I'll first take 100 of the data points. 100 of the data points. Suppose these are my 100. I'll fit a line. Okay, I will get some parameters w comma b for this. Right. I'll get some w comma b, and then I will take the next batch 100 to 200, and I'll again fit the model with my new parameters w comma b. Initially, my parameters for w comma b were totally random. I fitted 100 of my training examples, got w comma b, which this line, okay, and then I fit this. I like tweak this line for the next 100 training example, which are somewhere here. Suppose this line will shift a little, and you keep on doing that till till the end, till when you reach the end of the training examples that you have. Okay, so now that is called mini batching. I don't think anybody has doubts in this. So like, let's look at how the cost function will look like. So initially, when you were just like putting, okay, someone might ask this, like, why are we doing this? So that'll be a good question. Why are we doing this? Because what I would see, uh, what I think is, does anyone have any opinions? Like, why do we do this? Anyone? Yeah, think. Even I'll think. Now, in reinforcement learning, this is for linear regression. This was supervised learning specifically for linear regression. Now, how do you think we'll implement this for reinforcement learning? Anyone? Like, come on, like, now supposed to be obvious. Basically, whatever train data we have, we're trying to split it, right? So, relation, anyone? We split into many batches, yeah. Like, but what we split into many batches? The train data, but what is your train data? That's what I'm trying to get. That is the answer which I want to get from you guys. Yeah, the states. And if we go by the initial, what's it called, algorithm, which I taught at the start, which I discussed, but I'm not discussing with you guys, which I told at the start. If we go by that, then we'll split the states and actions into mini batches. Like we had 10,000 initially, we'll take 100 of them and then run the algorithm. Okay, so basically, what we are doing is we are taking 100. I mean, you're um, basically you're reducing. Basically, even I'm not very sure. You are basically reducing the number of training examples that you do on each, what's it called, repetition. When you're training your model, every time you're reducing the number of training examples you have. Basically, okay. So now that is mini batching. Like there'll be tasks. Okay, will I have to discuss with Shivanshu? Like, should we jump straight into project, because I'm not sure if the project is complicated. So we have to first discuss. Will me and Shivanshu will discuss, and then we'll figure out whether will jump straight into the project or we'll give you tasks first. And like honestly, I think it will be a good practice to first try to land a Mars rover by yourself. Like if that is a task which we give to you guys, because that is very interesting. And but the problem is, how will you guys visualize it? Like you guys need to visualize how the Mars rover is landing, right? You can definitely generate states and just put it in the neural network, but like exactly a game. But how will you convert that? Do you guys know development tools, like game development tools and all that? And I don't want you guys to waste a lot of time. If you guys are very interested, sure, but like if you guys want to do it together, it will be very nice. We can display it for open house as well. If you guys can kind of develop a game that can land a Mars rover, it'll be too cool. Okay, so but first we'll discuss. I mean, I'll discuss that. You guys also put it like if you guys really want to do it, sure, like put in group. Like you guys can do it together as well. So, anyways, so we'll discuss the next what's it called? I mean, I can just over it as this. It's called soft update. So, okay, no, I'll write it down only. Soft update. So remember at the end of this algorithm, where is the algorithm? Yeah, here. So at the end of the algorithm, our we are basically totally drastically changing from our old queue to our new queue. Right? We're totally changing. We have randomly initialized our queue, and we got a train data. We did training. We got our new values for queue for the state and action, right? But we're drastically changing it. Now, see, our reinforcement learning models compared to like supervised learning or unsupervised learning are very sensitive, and honestly it gets frustrating. Like right now when I was learning I was having full enthu and all, like, oh, I want to do this, that and so on. But initially when I tried to train my first model, that wasn't even reinforcement learning, that was just normal supervised learning model. It was a headache. I had to tweak my parameters, and I guess you also might have felt that when we gave you the tasks. So like, yeah, like tweaking the parameters and like trying to get a very high accuracy is very annoying. So and in reinforcement learning it's even more, because it is a topic where research is still ongoing, and many people haven't used reinforcement learning models as such. Like people are still under development, and yeah, like many people haven't explored the topic, I would say, haven't done research on the topic as much as any other what's it called, algorithm, supervised learning algorithms or unsupervised, right? So wait, where was that? Yeah, so we are drastically changing from Q new. I mean, drastically changing from Q to Q new. What I am saying is, don't do that. Keep some information of your previous Q. What I'm saying is, put Q is equals to some factor. Let's say 0. Okay, a good question would be is to how much of your previous Q should you put in your new Q. So I would say initially, not initially. I think a better, like even I'm not sure, but I think a better thing would be to first have a lesser amount of your old queue in your new queue, because we started with random initialization, right? So we kind of want our lesser information of our old queue to be there in this. So I'll say some 0.1 of our queue new. Wait, yeah, our q dash which we get will have less information of our old one and more information of our q new, and will keep increasing this and keep decreasing this, and we'll set this as the next, your y for your training examples for the next run. Okay, so that is called a soft update. It's called soft because you are not drastically changing from Q to Q new. You are slowly changing it. It's like soft updates, sure, not slow updates, soft update. Okay, and there are many more algorithms, but it's for now. I guess this is enough, and I'm not sure if all of you have even understood what understood. I'm not sure if you guys have understood most of today's session. So I'll anyway, Bhavi, like, is the recording, is it has it properly recorded? Cool. Like from what you told, from when you told you have recorded, it was proper, right? From after that. Yes. Cool. Okay, so you guys can either like see that, or you guys can explore the topic by yourself by browsing the internet or YouTube. There are so many resources. There is a course of Andrew and G as well. So, but that course is a very big course for just getting a feel of reinforcement learning and all the like optimizations algorithms, like soft update or mini batching or epsilon greedy policy or whatever. You can just watch YouTube videos, and they would explain probably far better than how I have explained right now. But yeah, I mean, will the next couple of tasks, which I think will be on the like will be we will only be giving you the code for reinforcement learning, and you guys will fill that, or you guys can do this, that you can like create a simulation kind of for landing Mars rover. Okay, so we'll discuss that. And any other thing, like any doubts that you guys have had from the session, anything you want me to repeat, is like I'll be here only. The session is like over only. So if you guys have any doubts, anything that you want to talk,